Hello, welcome to this series of lectures on course CH103. So we are now on chapter 15. Let me just start from the topic. We are on acid-base equilibrium. So we're going to cover the first two sections in this slide. The common ion effect. When you have an existing equilibrium and then a species that is common or that is already existing is added into the equilibrium, we have what we call the common ion. So we'll give you an example of this in this equilibrium. Let me reach out for my pen. So this is the equilibrium equation for the base dissociation. Okay, this is a weak base, ammonia, dissociates to form ammonium ion and hydroxide ion. Notice that these two ions are present in the product side of the equilibrium. So what will happen is this: if you add more ammonium ion into the mixture, it's going to shift the equilibrium backwards. And that's what we are talking about here in terms of common ion. So you basically add one of the ions, which is sold from a salt, like this case, ammonium chloride. So that's what we are doing in this section here, looking at the effect of adding common ion to an existing equilibrium. So another example will be this one. For example, this is a weak acid, nitrous acid. That's the equilibrium. It ionizes or dissociates in water to form hydronium and the nitrite. This is the nitrite anion. So what will be the common ion to be added here? You will need a source of this nitrite ion. So that can be added in the form of sodium nitrite. Sodium nitrite produces sodium ions and nitrite ions, and this is the ion that will be in addition to what is already in existence at equilibrium. So in other words, that will cause the equilibrium to shift to the left for this particular weak acid. So let's do the calculation here of one example of a common ion. An equilibrium concentration, the equilibrium concentration of H plus is 1 molar. The equilibrium concentration of H plus in 1 molar HF solution is given. So you're given the equilibrium amount and the percent dissociation is provided. Calculate the concentration of H plus and the percent dissociation of HF in the solution containing 1 molar HF. So we have the acid concentration given, and if you're going to add this common ion source, which is the sodium fluoride salt. So let's do the calculation for this one. So in the solution containing 1 molar HF and 1 molar NaF, the major species are, this is a weak acid, so HF will be the major species together with water. And in this salt here, the major species will be the two ions. And of course water, so water is also there. All right, so we have the major species and the equilibrium equation. Okay, let me just draw the equilibrium. And that's the ionization of the weak acid. And so Ka expression for that will be concentration of the products divided by the reactants, and we're given the Ka value. Okay, so what we can do is set up the ICE relationship or table. The initial concentration of HF is 1 molar. The initial concentration of fluoride ion is 1 molar. Notice that this comes from the salt, NaF, and initial concentration of H plus is 0. This is assumed to be 0 because water can contribute H plus, but we're saying that it is very negligible. Okay, so at equilibrium, it'll be 1.0 minus X. This one for fluoride will be, because this is a product, 1.0 plus X, and this is X. So the 1 mole that is produced, from the fluoride ions is coming from the salt. Remember that I mentioned above. Okay. So let's put it into the Ka expression, and you will see that X into 1 plus X and 1 minus X. Now, that is an important step here, which is the assumption that X is very small, so you can reduce that. So you end up this canceling out, you end up with X equals this. So X is small compared to 1. This result is quite reasonable. So that's the value of X. And therefore, we can work out the pH. The pH from the concentration is 3.14. And also we can work out the percent dissociation of this is 0.02. Notice that the percent dissociation really is also the test for the criteria less than 5%. So this is pretty well below 5%, which is a valid step in our assumption. So compare these values of H plus and the percent dissociation of HF with those of the 1 molar HF solution, where H plus is 2.0 times 10 to the power minus 2. So without the addition of salt, this was the concentration. Now, in the presence of the common ion, as we just calculated out, what was the concentration? Let me go back. In the presence of the common ion, notice that this value is much, much lower. So you see what we mentioned at the beginning, that the common ion basically pushes the equilibrium to the left. All right. So that leads us to what we now come into a major portion or major part of our discussion in this section here, and that is on buffer solutions. What is a buffer? It is a solution mixture that resists any change to pH. An example is the blood system in the human body is actually a buffered system. It absorbs acids and bases that is produced in the biological reaction without changing the pH in the body drastically. And the pH of blood in the body is roughly about 7.4. So, what is in the buffer? A buffer contains a weak acid with its salt. So I'm going to go through a few examples here in our discussion. So here's one example. A buffer solution contains the acid, this is acetic acid, which is a weak acid, and the salt of that acid, sodium acetate. What is the common ion in this buffer solution? Acetate. This one is produced by the salt and is also produced from the acid. Notice that. So the question is calculate the pH of this solution. All right. How are we going to go through this? Major species from the weak acid is the acid itself, molecular form. And for the salt, you have the sodium ions and the acetate ions. Those are the major species. And water being the medium is the also the major species. So it's a very weak acid or weak base. So these are the major species in this mixture. So the acetic acid dissociation equilibrium will control the pH, and let's look at that equilibrium. There. So ionization of acetic acid to the hydrogen ions to the acetate ion. Okay. So let's draw the equilibrium setup. So this is Ka. Ka is 1.8 times 10 to the power minus 5, and that is equal to the concentration of the acid, H plus acetate, divided by the molecular acid. So here's the initial conditions. The acetic acid is 0.5 molar, we're given that. And notice that this one, initial condition or concentration for the acetate is 0.5 molar. Where did we get that? It comes from the salt. And for the hydrogen ions, the initial concentration is taken to be 0. The reason is this, for this, because we are ignoring the contribution from water. Water will produce some of this, but what we're saying is that it's really, really small, so we can estimate it to be, approximate it to be 0. Okay, at equilibrium, it'll be, including the change, 0.5 minus X, and for the acetate ion, it will be 0.5 plus X. So look at this one here. Because of the pre-existing quantity, it's no longer 0 here like as we used to do in the past. This is now 0.5 as well, and you have to add X, which is the change. And of course, this one remains X, which is part of the ICE setup. So you'll see that in this ICE table, the initial condition for the acid dissociation to its ion components, 0.5, that is 0, that is 0.5, which is the common ion source from the salt, minus X, plus X, plus X, and now equilibrium will be 0.5 minus X, X, 0.5 plus X. So let's bring that in and substitute into the K expression. So you'll get X multiplied by 0.5 plus X divided by 0.5 minus X. All right. So just bring that into the Ka equation. And now let's do that very important step. Assume that X is very, very small. Therefore, you'll simplify this ratio, and it comes up to be canceling out of these two. So when you cancel out these two numbers, it gives us the answer. X is 1.8 times 10 to the power minus 5. And this is a small number, and therefore our assumption should be still valid. But we can always validate that. So approximation are valid by the 5% rule. X is equal to 1.8 times 10 to the power minus 5, and therefore a pH is 4.74. So that is the value of the pH of a buffer solution. Notice that the pH is calculated from the concentration of, notice that the pH is essentially calculated from the concentration of this acetate ion and this, the acid. So it's the acid and its conjugate base. So that leads us into this very important relationship, and that is the Henderson-Hasselbalch equation. Now I'm going to give you another example on calculation of the buffer solutions. Now this buffer mixture is slightly different from the one we saw in the previous example. Notice that This is ammonia with ammonium chloride. So what kind of buffer is this? This is a basic buffer. So if it's a basic buffer, you expect the pH to be greater than 7. All right, let's go ahead and do the calculation. What I'm going to use now, which will come later in the discussion here, is the combine steps. Instead of forming the ICE table, we have what we call the Henderson-Hasselbalch equation. What is the Henderson-Hasselbalch equation? pH is equal to the pKa plus log of the concentration of the base, that is a conjugate base, over the acid. Base over the acid. So I'll use this equation in this calculation. All right, let's go ahead and see. One point that you need to realize that Ka is not provided in this question here. Remember that Kb is given because this is a basic buffer. So we need to calculate the Ka because we're using the Henderson-Hasselbalch equation. How do we calculate Ka? From Kw. All right, so substitute those values out and it gives you the value of Ka. So now we can find out what pKa value is. pKa is 9.26. So to calculate the pH, pH is equal to pKa, which is 9.26, log of the concentration of the base versus acid. What is the base here? Is NH3 concentration, and this one is the concentration of NH4, which is the acid. NH4 is the acid. So what are the concentrations given? It is there in the question, so it's 0.25 over 0.4, and we get 9.06. So notice the difference. For this one, this is a basic buffer, and its pH is greater than 7. In the previous one, it's an acidic buffer, pH of less than 7. Now, one other step in this calculation that we can use another form of the Henderson-Hasselbalch equation, and that is the POH form. But I'd like you to note this equation very carefully. So we can write POH is equal to, instead of pKa, it'd be pKb plus log of the concentration. Now instead of the base above here, it'll be the acid divided by the base. So basically it's the reverse of what we've already discussed for the pH relationship. So notice that you can also use this equation. This is still the same Henderson-Hasselbalch equation, but written in the POH format. All right, so let's just try and do that from the previous example. POH will be equal to pKb. So since we are given the Kb, 1.8 times 10 to the power minus 5, change that, convert that to pKb, it's 4.74. Plus log of. Now, you see this ratio here? You see exactly the opposite of the ratio from the pH formula. So this one is now the numerator. This one is now, this one goes to the denominator. So evaluate this log ratio and take the log and then add it to 4.74. That's the value, 4.94. All right. Now, in order to find the pH, we still have to calculate that from the value of 14, which is the sum of the pH and the pOH. So pH will be 14 minus 4.94. Lo and behold, we get the same value. So you can apply the pOH formula or the pH formula of the Henderson-Hasselbalch equation, but you've got to be very careful on how you substitute the terms carefully. All right, this calculation here is going to be the next step. A buffer solution containing 0.5 mole acetic acid and 0.5 mole sodium acetate. Notice that we are going to calculate the change in the pH when you add 0.01 mole of sodium hydroxide. So we take the volume as a liter in this case to help us in our calculation, and we make it very simple by using 1 liter volume. So the question here is, what will be the change in pH when you add 0.01 mole of strong base? And later we will do the comparison when we add 0.01 mole to water. So 0.01 mole sodium hydroxide to water. So let's go in here. So the major species in solution for the weak acid is this, the acid, molecular acid, and in the salt it comes with this 2, and water, we have that in solution. And now because we're adding sodium hydroxide, we're going to be also bringing this in. Okay, so let me solve the equation. So what happens when we add sodium hydroxide into a buffer? So let me just write the equation. It'll be NaOH plus, in the buffer you have this let me erase that. Let me erase this one. So let me get back the pen. So HC2, H3O2. Okay, so that's acetic acid. And also in solution, you have sodium acetate, NaC2, let me just get on with this, NaC2, H3O2. Okay, the reason I put it in this form is for you to see it clearly. So when you add sodium hydroxide, question is, which reaction or which is the species that sodium hydroxide will react to? This is a salt. So, and this is an acid, right? The sodium hydroxide we know is a strong base. So where will the reaction take place? Between these two. So sodium hydroxide, when you're going to add it into a buffer, it will react with the acid. All right, so this is what happens. So this is the reaction. Sodium hydroxide, we're just writing down the hydroxide, reacting with an acid, it will produce water and the anion, which is when you take a proton from here to form water, you form the anion. So that's the anion. So it's a typical acid-base reaction. So when it's an acid-base reaction, we will consider their mole ratio or mole quantity. Mole ratio, this is a 1-to-1 ratio. So we've done this, and you should be able to follow through the stoichiometry for that one. So then, so we follow the stoichiometry. So this is the initial quantity of the species. For the acid, is a liter of 0.5 molar, so it's 0.5 mole. You're adding 0.01 mole of sodium hydroxide, and here you have a liter of 0.5 molar, so that will give you 0.5 mole of acetate. So that's before the reaction, before you add any hydroxide. So remember, you are adding hydroxide to a buffer. So this is before you start the addition, you're going to have that sort of setup. Now, after the reaction, this hydroxide will react with the acid. Notice that it's the same stoichiometry. So it will consume 0.01 from here, and that will take away 0.01, which will lead to 0. And likewise here, it will be added with an increase of 0.01. So now we have the new quantities after the addition of a 0.01 mole base. So 0.49, 0.51. So when we have that sort of new quantities, we can now put it into the ICE table or the Henderson-Hasselbalch equation. So let's bring in 0.49, 0.51, and now let's repeat the ICE setup. Minus x plus x plus x, and that will give us this equilibrium values. Notice now, after the addition of base, we come to this new position. All right, now we can solve this in the same way. So Ka is 1.8 times 10 to the power of minus 5, and then substitute those numbers in. Notice now, this changes from the addition of the base, and we see that this ratio is changed slightly, and it becomes 0.51, 0.49 when we make the assumption. And now it becomes x is equal to 1.7 times 10 to the power minus 5. And that should be still valid based on the 5% rule that we've been discussing. So that gives us the pH of 4.76. All right, notice now what we had at the beginning is this. 4.74 was the original solution from the mixture itself, that is just on the buffer. And when you add the 0.01 molar of base, it increases to 4.76. So what is the pH difference? 0.02. Okay, now watch this very carefully. pH is increased by 0.02 units. Now let's compare that when we add 0.01 mole, same amount, in water. Let's take 1 liter of water, and that's where we add 0.01 mole of sodium hydroxide. What do we get? So let's work out the concentration. In 0.01 mole hydroxide, we can work out the pH. That's how we work out the hydrogen ion concentration. That's a pH of 12. Kw over OH concentration, that is 10 to the minus 14 over 10 to the minus 2, and that gives you 12. Now, notice that this change, when we add 0.01 mole in a liter of water, it gives the concentration of this solution. And that concentration is what we've now calculated its hydrogen ion concentration, which gives a pH of 12. So addition of 0.01 mole into a liter of water, of sodium hydroxide into a liter of water, produces this pH. What is the pH of water? pH of water is 7. Addition of 0.01 mole of sodium hydroxide gives 12.00 as a pH. So the change in the pH is +5. So notice the difference in the changes on pH. In the previous one is 0.02, which is in the buffer solution. In the unbuffered, a change of 5 pH units. That's a big difference of the two. So you can see the role played by the buffer when a strong base or a strong acid is added. So let me just summarize. In solving buffer problems, buffer solutions are solutions of weak acids or weak bases containing common ion. When a strong acid or base is added to a buffer solution, it is best to deal with the stoichiometry of the resulting reaction first. So original buffer solutions pH. Step 1, do the stoichiometry when you add a strong acid or strong base, and then do the equilibrium calculations, and then you see the modification of pH. So the buffer solutions, really, if you add any strong acid, the conjugate base from the buffer mixture will interact with that acid, and vice versa. If you have add a strong base, it is the acid from the buffer mixture is what will interact with that strong base. So essentially, in the buffer equation, which is shown here, this is the equation of the ionization of a weak acid. If we rearrange this and make H the subject like this, so take Kn to the other side and H, this will lead us to essentially this form. So if you write the equation with H as the subject and taking the negative log on both sides, it will lead us to this relationship here, and you'll find that that basically is how we derive the Henderson-Hasselbalch equation. Okay, that concludes the first part of this lecture. Thank you.